All right, moving on in chapter 40. So chapter 40, right now we're looking at molecules. Our previous lecture, we took a look at chemical bonds, the types of bonds that hold molecules together. Talked about how pairs of electrons end up in molecular quantum states. So we have wave functions that represent those molecular quantum states. And now we're ready to move on. And rather than looking at the chemical bonds holding the different atoms together, holding the different nuclei together, what we're going to look at is the molecule as a whole. Because there are a couple of different types of energy associated with molecules as a whole. One of those is rotational. So, classically we would think, sure, molecules can rotate, and when molecules are rotating, that corresponds to a certain amount of rotational kinetic energy. Well, there's a quantum version of that, and we'll see what the properties of those are. The other one we want to bring up is along any chemical bond, there is the possibility of what we call vibration. Vibration corresponds to variations in the distance between the nuclei. So for example, let's see what those energies might look like. They're calling this molecular spectra. We're really looking at the energies, the rotational and vibrational kinetic energies of the molecules. So here's an example of a diatomic molecule. So we're going to start with the simplest examples, and that's really about as far as we're going to go. So we're only going to look at diatomics, things like H2, N2 nitrogen, O2 oxygen, carbon monoxide, CO, that's diatomic. Now, if we have a diatomic molecule, when we think about rotational kinetic energies are associated with mass in motion. And if we look at a molecule, the mass is pretty much all in the nuclei. The electrons contribute a tiny fraction, less than 1,000th of the mass in a molecule. So in order to determine the kinetic energies of rotation for a molecule, we really just have to look at the nuclei. So we've got this diagram set up. So here is nucleus number 1, which we're assigning a mass of m1. And here is nucleus number 2, which we're assigning a mass of 2. Now what's not shown here are all the surrounding electrons. So we're going to have an electron cloud, a bunch of electron wave functions that envelop these two nuclei. And in order for a chemical bond to be here, there's got to be a good amount of electron probability, a good amount of electron probability density in the region between the two nuclei. That's what we saw in the previous lecture. So we're going to kind of ignore the electrons. We know they're there. And what they've looked at here is they've said, okay, let's imagine a rotational axis. Now, for the rotational energy, we're going to move into the center of mass reference frame for the molecule. We're going to treat it as if the molecule is just sitting there, rotating, and then quantum mechanically we're going to ask what are the quantum states for that rotation going to look like? How much energy will there be? So here's our rotational axis. Let's, so the other items here, R1, distance from the center of mass out to nucleus 1, R2, center of mass out to the center of nucleus 2, so out to the centers of the nuclei, and then R as a whole is the distance center to center between the two nuclei. It's the bond length is what that's keeping track of. All right, here's my own version of that. So I'm calling it rotational energy for the molecule, and reminding myself that we're just going to look at the diatomics. We're not going to look at anything more complicated. And so here is that same diagram. Here's nucleus 1, nucleus 2, mass 1, mass 2. The distance between the two nuclei is R. Now there is an R1 here, there's an R2 here, but we want to be able to work in terms of the distance between the nuclei, the bond length. Now, a quick review from Physics 4a. If you remember, rotational kinetic energies could be written as 1/2 times a rotational inertia times omega squared, where omega was an angular frequency. Now that's one way to write this. There's a second way. What we can do is, instead of writing in terms of the rotational velocity, what we can do is we can write in terms of angular momentum. That's an L, that's angular momentum. And if you remember, when we first introduced the Schrodinger equation and talked about linear kinetic energies, we said that, and introduced operators, we said that velocity doesn't play a very important role in quantum mechanics. It's momentum that actually is represented by this operator, IH bar, partial derivative of x. And so it turns out rotationally the very same thing happens. It's not angular velocity that plays the important role, it's angular momentum. And we've already seen that with atoms, specifically the hydrogen atom, when we went in and looked at the rotational, or the angular momentum states for atoms, for electrons inside atoms. Well, now we're looking at the whole molecule and saying the entire molecule is going to have some amount of angular momentum. That kinetic energy of rotation can be written as 1/2 L squared over I. Now we already, I guess we know this, we didn't really solve it in a lot of detail, but what we found with angular momentum in general, not just angular momentum for electrons in atoms, but in general, all through nature, angular momentum is quantized. So when we get down to the level of individual particles, electrons, protons, atoms, molecules, nuclei, the angular momentum squared is given by a set of quantum numbers where the quantum numbers possible, quantum numbers here, are starting at 0, any integer value of L. And so what we've got here then is L squared, the actual amount of angular momentum squared, is given by some quantum number times h bar squared. And remember, h bar has units of angular momentum. It's kind of a natural quantity of angular momentum to work from. So what that gives us then is a kinetic energy of rotation formula predicted in quantum mechanics as L plus 1, h bar squared over 2I. And now, something that we recognize as purely kinetic energy actually gets written as big E. Just a warning, here's another example of, oh my gosh, we've defined big E several different ways through this course, or through the whole 3-semester series. This time the big E of rotation that they're talking about is purely kinetic. So something you should be aware of. And that's the formula, and those are the possible quantum numbers. Now what this does say is, if I try a couple different values of L, and I write down how much angular momentum that corresponds to, another erasure, sorry about that. If the quantum number is 0, then there's no rotational energy. So that's kind of interesting too. A lot of times in quantum mechanics, there's a lowest energy state, but it's still a finite amount of energy. With rotation, it's possible with angular momentum. It's possible that you just don't have any angular momentum at all. So there are these spherically symmetric wave functions that correspond to no angular momentum. All right, if we jump up to state 1 and plug in a value of L equals 1, then 1 times 2 over 2, the 2's cancel, and it says that the first excited state of rotation is 1 unit of h bar squared over I, where I is the rotational inertia again. And then for state 2 and 3, those numbers become 3 and 6. So what we're seeing is this. If we look at the spacing, we've got this lowest rotational energy of 0, and then we have to jump up like 1 h bar squared over I to get to the next state. Then we have to jump up to 3, and then we have to jump up to 6. So what's happening here is the spacing between the rotational excited quantum states is getting larger and larger. So that'll be important when we do look at the photons that can be absorbed or the photons that are released due to rotational quantum state transitions. These are the numbers that we'll work from to determine how much energy those photons would have. Now it turns out with rotation, it turns out with angular momentum in general, that the most likely transitions are where the angular momentum changes by 1. And the reason for that is photons have 1 unit of angular momentum. So if a photon comes in, it's going to transfer that angular momentum to the atom or to the molecule. Now, what that can do is it can cancel, it can offset the angular momentum that the molecule already has, or it can add to the angular momentum. But in general, I don't know, 90-something% of the time or more, these transitions are just one step at a time. So that says that, let's say that we want to send in a bunch of photons and get the molecule excited into state number 3. Well, we're not going to do that with just one photon. We're going to have to do that in 3 steps. Send in a photon, boost it up to state 1, another photon, boost it up to state 2, another photon, boost it up to state 3. The reverse process would be the molecule would emit photons in those 3 steps also. All right, just a reminder here too. We kind of know what h bar is. That's a physical constant we look up. Rotational inertias. Now, the rotational inertia would come from taking m1 times r1 squared plus m2 times r2 squared. I didn't go through the whole derivation. I thought maybe we don't need to do that. In any case, and I don't think you necessarily need to do that, it's an interesting exercise you could go through. I think it's outlined possibly in our textbook. In any case, what happens is the combined effect of rotational inertias from both of those nuclei is that the rotational inertia can be written in terms of something called the reduced mass. So mu is called the reduced mass, and it turns out that mu is given by m1 times m2 over m1 plus m2. If you carry out the algebra, you see where that comes from. So that says that in a molecule, let's say it's carbon monoxide, for example, we can look at the mass of the oxygen, the mass of the carbon, plug those into our reduced mass formula, and then put in the bond length, square it, and that'll tell us how much rotational inertia we have. And then that is what gets plugged into our rotational energy formula. Now you might be wondering, well, what about the monatomics? Don't individual atoms rotate? And they don't. So we don't have rotational energy states for individual atoms. In those cases, the nuclei are at the center, and there's essentially no rotational inertia. The wave functions that we've defined for electrons already take their angular momentum into account. So any rotational effect of the electrons is already taken care of. And so, yeah, it's like rotation just isn't defined in quantum mechanics for monatomic atoms. So we have to get up to this diatomic level before we start to see these additional effects come into play. Now, as we were saying from that previous diagram, if we look at the different possible values of L, and here we've gone from L equals 0 all the way up to L equals 5, these are the possible values for rotational kinetic energy for the diatomic molecule. And the energies start off at 0, and then everything can be written in terms of h bar squared over I, the rotational inertia. And so what we've got here is one of those units, and then 3, and then 6, and then 10, and then 15. And yeah, there's a pattern here. If we look at the spacing between those quantum states, what we see is it increases in a linear fashion. So the gap between state 0 and state 1 the delta E is equal to h bar squared over I. The next gap is at 2, the next at 3, 4, and 5. Check the numbers and see. Those are the energies of photons that would be absorbed in going from one state to the next. And so, yeah, we can predict. Now, this is where the molecular spectra comes in, is we're saying, okay, if we send a bunch of photons into these molecules, which ones get absorbed? And the photons that get absorbed are in these energy range. Now, what part of the spectrum of light corresponds to energy spacings for rotational states? And this is kind of in the microwave part of the spectrum. It turns out that the spacing for these rotational energy quantum states, it's pretty small. When you put the numbers in, you see that these energy gaps are pretty small. But they tend to be in the microwave region. In fact, our microwave ovens are specifically designed to excite water molecules. So the reasoning here is that, hey, all kinds of food have water in them. As long as the food has water in it, we can put it in the microwave oven, turn on the microwaves, we flood the chamber with a bunch of microwave energy photons, and those photons, the oven's been designed so those photons have just the right amount of energies that they can excite the water molecule. And then from there, those water molecules can transfer the energy into the surrounding molecules, and all of the food heats up eventually. The water molecules get heated up first. We're specifically going for these quantum state excitations in the water molecules. All right, so that's the energy spacing. Here we are with that reduced mass. So that's worth taking a quick look at too. Reduced mass, we said that the rotational inertia can be written as mu times r squared with the reduced mass defined this way. Again, if that's something you want to go in and take a look at and try and derive, it's fine. If you've got questions, let me know. And I can write up a solution to that and scan it and post it. So I can get something up online if you guys are interested in the derivations on that. All right, that's how the reduced mass works. We need the bond length and to get the rotational inertia from that. So here's our example. So let's go in and do some numbers for rotational energies. Now, the example that they've given us is with carbon monoxide. So in a carbon monoxide molecule, it's diatomic. I got a carbon nucleus and I've got an oxygen nucleus. And there's a certain bond length between those two. Now, it says that we are looking specifically at the L equals 1 to L equals 0 transition. So we're looking for that lowest energy spacing between the ground state and the first excited state. They want us to be able to go, so they've told us this information. They said that when we take our sample of carbon monoxide into the lab, be careful, don't inhale that. If we take our sample of carbon monoxide into the lab, we find that at a wavelength of 2.60 millimeters in the microwave region, we see this absorption take place. So we put a bunch of carbon monoxide in there that's all in the ground state. Maybe we've cooled it down to a very low temperature, and we send it in a range of different microwave energy photons. And if all the molecules are in the ground state, then the only absorption rotationally that can be taken in is the 0 to 1 rotation, or the 0 to 1 transition. So, so what it says is this specifically is for this transition, and can we calculate the moment of inertia? Can we calculate the bond length? And then finally, can we predict what other photons will be absorbed by carbon monoxide molecules, specifically for rotation? So let's get in and take a look at this diagram, this example. It looks really good. So, and I have to say, I do like these examples of rotational and vibrational energies. I think they're really useful items that very relevant for the course, and anyway, something you guys should understand pretty well. Now for carbon monoxide, the first thing I have to do is write down those masses of the two nuclei. Now, if we have different isotopes, then we have to decide which isotope we want to work from. Carbon, for example, there is a small amount of carbon-13 in nature, and you go, well, is it carbon-13 or carbon-12? Because if I use a different isotope, that would give me a different rotational inertia. It'll give me a different set of quantum states, energies. So it's the same set of quantum states, but the energies will be different depending on which isotope we use for the carbon and the oxygen. Now I've picked the most common isotope for each, but just a reminder, this is not something that we pick off the periodic table, right? The numbers on the periodic table are averaged over the different isotopes. But when we're doing predictions of energies, each pairing of isotopes is going to have a little different set of energies for their quantum states. So this is specifically in terms of the 12 isotope of carbon and the 16 isotope of oxygen. Now, carrying out this reduced mass formula that we talked about, that gives me a value of 6.86 atomic mass units for those individual molecules. And then a quick reminder of the conversion. The way atomic mass units and grams and kilograms are defined, 1 gram is Avogadro's number of atomic mass units. And when you stop and think about that, you go, oh yeah, that would have to be the case. If I have 1 atom of carbon, it's going to have a mass of 12 atomic mass units. If I have 1 mole of those atoms, it's going to be 12 grams. So I don't have to necessarily remember a new constant. I can use Avogadro's constant to carry out these conversions. Now, with the formulas we're working from, we want to get back into standard units. We don't want to use grams. We want to use kilograms for the masses. And that says instead of just a mole, we want to use a kilomole. So 6.022, 10 to the 26. So Avogadro's number is going to be the conversion that we want to use. All right, so what I did was I took the 6.86 and converted that into kilograms, and there it is, 1.14, 10 to the minus 26 kilograms is the reduced mass. And it's a tiny, tiny number because it's just 1 atom or 1 molecule that we're looking at. Now, oh, that was the first part of the problem. I think I got the A, B, I got an A sitting here. I don't know how that figures in. Anyway, this was part A of the problem. Part A of the problem was solving the reduced mass, and we've got it. Oh, I guess it was the rotational inertia we had to come up with. That's what it was. So maybe we need to step over here. Oh, and the diagrams too. Let me get back to those really quickly. Nucleus 1, nucleus 2, R1, R2, R. And then here is the transition. We're going to be, I think they intended this to go the other way, starting in the ground state and going up into state number 1 with a photon coming in. In either case, the energy of that photon is going to be the difference between state 1 and state 0. That's going to tell us how much energy we have for the photon is the difference between the two quantum states. Now, oh, we do need to, I see. Okay, so let's go back to here. I guess we don't have the bond length. We're finding the bond length. So let's do this. What we'll do is we will calculate the energy of the photon. We'll use that information and say that's equal to h bar squared over I for the molecule. Now, the other way that we can determine how much energy that photon has is they gave us information about its wavelength. And so the wavelength they gave us was 2,600 nanometers times 1,000. So this was actually in millimeters. And so I put some couple factors of 1,000 in there. And so that told us that the energy of the photons is 0.477 times 10 to the minus 3 eV. Now that's a small number compared with the energies we were seeing for electrons in atoms. When we looked at electron energy states in atoms, those were many, many eV, and now we're seeing that the rotational energies are tiny, tiny fractions of an eV, so the spacing is really small. Let's see, so that's the energy of the photon, and what we can do is we can use the energy of the photon to determine what the rotational inertia will be. So since the energy of the photon is related to the difference between the two quantum states, and that's h bar squared over I, we can actually use that relationship where it says part A and solve for the rotational inertia. And that tells us that the rotational inertia for this carbon monoxide molecule is 1.46 10 to the minus 46 kilograms meters squared. So that's in standard units, and it's a tiny, tiny number in terms of kilograms and meters, as you would expect. Now, once we've got the rotational inertia figured out, then we can use the rotational inertia formula in terms of bond length and in terms of reduced mass to determine what that bond length is. So here I've taken the rotational inertia that we determined from observation, from seeing which photons get absorbed, and then our reduced mass calculation comes from just knowing which nuclei are we dealing with. And that gave us a bond length of 1.13 10 to the minus 10 meters. That's 113 picometers. That seems right. You know, that is the size of these molecules. So when you look at these relatively light atoms, bond lengths between carbon, oxygen, nitrogen, hydrogen, they're in the range of 100 picometers or so. And maybe some of you familiar with chemistry too are aware that carbon monoxide has one of the strongest chemical bonds of all materials that we look at. It's considered to be a triple bond. It's got a fairly short bond length. It's a pretty stable molecule. All right, so that worked out. We were able to get the reduced mass. We were able to figure out the bond length. Now, what does happen in these other transitions? So what we've solved for in terms of photon energies, or the information that was given, was for the transition 1 to 0. And what we know is that from our diagram from before, let's go back and take a quick look at that. From the diagram that we had here, we're solving for the energy difference between those states. We know that this transition is twice as much energy, and this transition represents 3 times as much energy. So we can just do ratios on that. So what we can do is come back to here and say this first transition represented a certain amount of energy, the next is going to be twice as much, the next 3 times as much. What that's going to mean is that the wavelengths of those photons are going to get shorter by those very same factors. A photon with twice the energy has half the wavelength. A photon with 3 times the energy has 1/3 of the wavelength. So we can take the 2.6 millimeters, divide it by 2, and then divide it by 3 to answer that question about how do the wavelengths compare for the other transitions. What will be the wavelengths of the photons needed to make those additional jumps into state 2 and then into state 3. All right. So that was kind of our example with rotational energy states. And now what we want to do is we want to start looking at vibrational energy states. And I hope the word, there it is, the word vibration is here. The stuff at the top a lot of times kind of throws us off. But this is specifically looking at vibrational quantum states inside a diatomic molecule. Now for diatomic molecule, let's get the diatomic molecule back out here again. I've got nucleus 1, I've got nucleus 2, and what happens is that there can be kinetic energies of those nuclei shifting back and forth inside this envelope of electrons. So there's the electrons that are surrounding the nuclei, and you've got the nuclei shifting back and forth inside those regions. If we look at the bond energy, so this U is keeping track of bond energy. Now they're calling this the H2 molecule, but it could be any molecule as far as kind of the shapes that we're working at. The specific numbers they're looking at do correspond to an H2 molecule. So an H2 molecule has a bond length of 74 picometers, and it has a binding energy of 4.5 eV. All right, so actually probably minus 4 eV. What they're saying is that there's this energy profile as the two atoms come together. The energy drops. Two hydrogen atoms will come together and form an H2 molecule without any activation energy. So the H's come together, form the H2 molecule. Now, they don't collapse to zero length. So you would go, so somehow what's happening is, as these atoms come together, the nuclei and electrons from the opposite atoms are attracting each other in a way where those two nuclei are drawn closer together. Now, in the earlier lecture, what we had talked about a little bit, and let me review that a bit here, is that at some point, the electrons are as closely packed as they're comfortable being. If you remember, I guess, chapter 38, in quantum mechanics, the first quantum mechanics, full-blown quantum mechanics chapter, what we found out was that if you take particles and pack them into smaller and smaller regions, it requires that their kinetic energy go up. In fact, we said that's why solids and liquids are non-compressible, because in solids and liquids, the electrons are already as closely packed as they're comfortable being. If we continue to pack them even closer, we have to put energy in order to boost the kinetic energies of those electrons. Now the nuclei are really tiny, so their kinetic energies are not affected by this compression, but the electrons are. And so what happens is that creates this repulsive effect. So it's not that the pluses and the minuses, the plus and the minus charges necessarily start repelling somehow, where before they were all attracting. It's because now the electrons are as closely packed and they're not able to follow along with the collapse. So they end up preventing that effect. All right, so that's what the energy profile looks like. Now what we do quantum mechanically is this. We take this, reasonably complicated energy profile that keeps track of the energy as two hydrogen atoms come together, and we replace it, or we approximate it, with a parabola. Now in your calculus classes, you guys have done like Taylor expansions and Maclaurin expansions, and that's kind of what we're doing here. In order to get a parabola representation of this, we would be doing a Taylor or Maclaurin expansion, where at first, the first term in the expansion would give us the energy here, the minus 4.5 EV. The next term goes away in the expansion because the slope at that location is 0. And so the next term in the expansion is 1/2 kx squared, and you go, oh, that looks like the formula for the energy, the potential energy of a spring, and it is. So any kind of vibrational system, once we've identified where the equilibrium distance is for that system, the first term in the expansion that we can use is 1/2 kx squared. So we said, back in physics 4a, we said 1/2 kx squared, that's like an ideal spring. And now what we're saying is if we look at the vibrational energies of these atoms moving back and forth, or these nuclei moving back and forth in a molecule, that we can approximate that also as 1/2 kx squared. Now what they've got drawn down here is that the lowest possible quantum state is not going to be at that very lowest position. And that's because even though the bond length is 74 picometers, this vibration means that there's a probability at any given time that the bond length is a little longer or the bond length is a little shorter. That's what quantum mechanics is going to say, is there's not a fixed distance between the nuclei. The nuclei actually can be found at a variety of different distances from each other. The 74 picometers turns out to be the average bond length. If we do a series of measurements on these hydrogen molecules, we're going to find a range of different bond lengths averaging around 74 picometers. So that first quantum state is going to be up at, what it's saying is 0.5 eV. So we'll see if that is what this works out to be. All right, here is the vibrational energy setup. Now, where this all comes from, let's see. Here is nucleus number 1, here is nucleus number 2. Here is what we're going to call the bond stiffness. And so the bond has a K value, a spring constant to it, which tells us how stiff the chemical bond is. Now, if the K value is really high, then that says that the amplitudes of vibration are really small. There's not much amplitude of vibration allowed. If the K value is really small, then you can have much larger range of, larger amplitudes of vibration. Now again, this is quantum mechanics, so it's not like there's a well-defined trajectory. It's not like we can follow the nuclei vibrating back and forth. It's just saying that there's a probability of the bond length being larger, there's also a probability of the bond length being shorter, and on average there's some kind of most likely length for the chemical bond. Now looking at that system, what we can do is we can bring back the Schrodinger equation and say, all right, I want to find out what the energy is for these. In some ways we shouldn't even be calling it vibration, right? If there's no well-defined trajectory. So the whole notion of vibration here is a little misplaced. But there's a vibrational energy, and it's going to be represented by some quantum state. And here is the kinetic energy term. So it includes kinetic energy effects. And then for the potential energy, we're going to put in 1/2 kx squared. So 1/2 kx squared is telling us how much potential energy we have. That's what we saw in the previous slide. This is telling us about the potential energy effects due to this variation in bond length. Now, if we look at that energy profile, 1/2 kx squared, and draw that, what that says is as we move up in energy, there's a larger and larger possibility for amplitude of vibration. What it's saying is there's a wider and wider range of possible values for our bond length. So in the ground state, that wave function is going to have one peak right in the middle. So thinking back to the infinite potential well, for example, it looks kind of like the states we had for the infinite potential well. The difference here is instead of having absolute walls of fixed length, what we're seeing is that there's going to be a region inside that parabola where we're going to get these curves, these sine functions, sort of, something that looks kind of like sine functions in there. And then once you're outside those regions, since the potential here is finite, it's not infinite, we're going to have exponential drop-offs. In any case, what this is going to lead to is, for that 0th quantum state, most of the amplitude is in the middle, and that means most of the probability will be in the middle. For the first excited state, above the ground state, we're going to have amplitude that's kind of split. There's a node in the middle, and it says if you're in the excited state, the first excited state for this vibration, then there's a probability of the bond length being larger and a probability of the bond length being shorter, but there's actually no probability of the bond length being its averaged value. And then as you go up to the wave function here, 3 regions of amplitude. To calculate probabilities, we square that, we modulus square, and that would give us 3 sort of distinct regions of probability for a certain value of the bond length. All right, so it does derive back from Schrodinger's equation. Now, we could go through and solve that. We're not going to. What we're going to do is write down the results. Turns out that when you solve this equation, the Schrodinger equation for parabolic potential energy, what you end up with is a series of quantum states that have the, well, this is the common way we write it, v plus 1/2 times h bar omega, where v takes on any integer value, 0, 1, 2, 3, any positive integer value, and that the omega that we've written here is sort of the equivalent. Classically, what omega corresponds to would be the vibrational frequency. Now again, there's not a trajectory taking place, so this whole idea of vibration and frequency of vibration is a little misplaced. But what it does say is it predicts that there's going to be a series of different energy quantum states that are associated with the probability of different bond lengths within the molecule. Okay, and here I've kind of outlined what happens here. Right here in the middle is where the bond length is equal to the designated official bond length, the average value. And then the x in 1/2 kx squared is how far we've departed from the equilibrium position. So the same thing that we had defined for springs, you know, if we had a spring and we stretched it out at some equilibrium position, then we would call that x equals 0, and then we would start doing measurements from that. Same thing here, x is keeping track of departures away from the equilibrium distance between the nuclei. All right. And here's what that formula provides for us. So that formula that we looked at on the previous page, the lowest possible quantum state would be, here's the formula right here. Solving the Schrodinger equation gives us a series of quantum states. The energies follow this pattern. I've written it as h bar omega. The slides here have it as h times the cycles frequency. Same thing. I'm just working in terms of radians. They're working in terms of cycles. But notice when v is equal to 0, there's still leftover energy of vibration in that molecule. So that's kind of interesting. You know, it's saying there's a 0-point energy. I don't know if you guys remember the original movie, The Incredibles. They did a really nice remake a few years back. But the original Incredibles go way back. And there was a kid in there that was, I guess he was the, I don't know, he was the scientist that had gone kind of mad. Anyway, he had learned how to access the 0-point energy, and it made him super powerful. But that's what 0-point energy says is, hey, if we went and took this molecule all the way down to absolute 0, shouldn't all the energy be gone? And quantum mechanics says no. As far as rotation, the prediction is yes, all the rotational energy is gone, but there's always going to be residual vibrational energy. And the electrons are always going to have residual kinetic energies. So there are going to be these energies that are still present at absolute 0. So classically, absolute 0 meant all the molecules stop moving. Quantum mechanically, absolute 0 says everything has dropped into the lowest available quantum state. But there isn't anything lower. That's as low as they can drop. All right, so that's the formula. And what that's predicting for us is a series of different energies. So if I look at the V values again, 0 through 5, then these are the energies of those quantum states: 1 half, 3 half, 5 half, 7 half, 9 halves times HF. So, and remember, frequency is related. I've got to take a step back and look at this too. How was frequency defined? Because frequency doesn't really have a meaning for these molecules. Frequency is defined as the bond stiffness divided by the reduced mass. So that's something we also saw in classical physics back in Physics 4a. And so we can think of that in terms of, again, bond stiffness and the reduced mass we've already taken a look at. So that's what the energies are going to depend on. The energies of these quantum states, where you see the frequency, you go, and that frequency variable depends on how stiff the chemical bond is, and it depends on what the reduced mass is for the nuclei that we're looking at in our diatomic molecules. All right, what does it say about photons that are being generated? And it says that, to first approximation here, 0th approximation, all these energy spacings are the same. And that says that if we kind of do this one step at a time, as we did with rotation, if we do transitions here one step at a time, that all the photons will have essentially the same energy. And that is the case. Again, the rules for transition for vibration say that molecules take one step at a time. They don't skip steps. And so all the photons that we use to excite the molecule, all the photons coming out when the molecule is losing its energy, those are all essentially the same value. All right, so here is that diagram again. We saw this for hydrogen. Now what they want us to do is go in and get some values. So they're telling us that, in this example, they're saying actually use the curve that we have here to figure out what K is. So I don't think we're going to take a look at this one. It's really just determining what that dashed line parabola, what the values are, so you could go in and estimate the bond stiffness from that. The example we want to take a look at is this. So let's look at the energy quantum states in hydrogen for vibrational energy. And what we're finding is that the photons that are being radiated or absorbed are at 2300 nanometers. So remember that the photons are the key to all this, right? When we go into the lab and we analyze these different compounds, we shine light at them and we see what gets absorbed. And then we shine light at them and we see what they radiate back out. And in this case, what we're seeing are photons with a wavelength of 2300 nanometers. Now this is in the infrared region. So when we looked at electron quantum states, those were like in the UV and the visible light. When we looked at rotation, they were like in the microwave, really low energy. Vibrational energies are kind of in the middle. They're not as energetic as the electron quantum states we looked at, but they're much more energetic than the rotational transitions. All right, so let's see what that leads us to here. And we're getting pretty close to probably time we should take a break here, but I'll probably just get this set up and come back in the next segment, in the next lecture, and go through this example. So let me do that. Let me end right here. We're just getting in. So the example we're going to want to start with in the next segment is looking at vibrational energy for quantum, vibrational quantum states in hydrogen molecules. Oh, I actually do have just a couple minutes, so I'm going to see how far we get through this. Sorry about that. So let me get part of this set up. So we're going to bring in our vibrational energy formula. And we're going to apply this to hydrogen. We're looking at these quantum states going from state number 1 down to state number 0, thinking in terms of the energy of the photons. Energy of the photons are given by hc over lambda, so that's our old friend 1240 eV nanometers divided by 2300 nanometers. That gives us an energy of the photon of 0.539 eV. So we now know, using the wavelength, it wasn't a big deal, but we converted that wavelength over into photon energy. So that's telling us what the spacing is between successive quantum states of vibration. Now, we're specifically looking at the 0 to 1 transition, and coming back to this formula tells us that the ground state is at 1/2 h bar omega. Well, h bar omega turns out to be the same amount of energy, the delta E, the energy difference between the two quantum states. And so what we can do is we can substitute in the energy of the photon right here. This is the spacing between the quantum states. The ground state is 1/2 of that. The excited state is 3/2 of that. So those give us the energies for the ground state and for the first excited state. So in any case, what that is telling us then is how much vibrational energy do we have in those states. Coming back over here, here's our diatomic molecule. Here is the stiffness of the bond, and we can calculate the stiffness of that bond. We can calculate it as mu times omega squared. So I went back and calculated reduced mass. Now we've done that before. So we looked at that with carbon monoxide for rotational states. And what I got for an H2 molecule was this, 8.37, 10 to the minus 28 kilograms. I can now, again, working from the formulas that we have here in terms of the photon energies, what we can do is calculate that omega as the energy of the photon over h bar, and this gives us a value for omega. I plug that into my K, and I'm ending up with 559 newtons per meter. So that's how stiff the bond is in hydrogen. All right. So we figured out what the energies are of vibration for those lowest two states, the ground state, first excited, and here we have the bond stiffness for the hydrogen molecule. All right, and now we should definitely stop, and I'll move on to the next lecture.